Okay, can you see that?
Yeah.
Okay, so I'm going to talk about parameter estimation in COPASI, and as you had seen in earlier talks, this parameter estimation is also available in vCell. So I'm going to have only very few slides. I'm going to do that more on practical examples because we're going to see the pitfalls and what needs to be done there better than when I try to explain that to you in detail and just theoretically. So first of all, the parameter estimation is a specific problem of optimization. Optimization attempts to maximize or minimize the function. In other words, it's try to find parameter values for a function to which the function attempts to finds a minima or maximum. So we can give boundaries on these parameters, which can be inequality constraints. Normally you have boundaries, parameters less than a certain value or bigger than a certain value. And you can have equality constraints. So one parameter needs to be another. So, and important is if you do optimization, if you can minimize, you can always maximize because it's the minimum is the maximum of the maximum is the minimum of the negative of the function. So what I'm talking about in the future is I'm talking about minimizing, but that's not a constraint. So down there, down here, you just see how that actually applies. So if we optimize, what is the approach? In general, we have some functions which we want to evaluate. That's called the objective function. We have an initial guess of parameters for this function. We do an evaluation. It can be time cost, it can be a steady state, it can be all kinds of things. At this moment, it's very generic. And then we check whether the solution, the function value, is actually satisfactory to us. If not, we start with the optimization and we determine new parameters, values k. And this optimization, that's where different methods come into play, which I'm going to talk about in the next slide. But they give you a new guess of parameter values. We evaluate the function for these parameter values, and we check whether that satisfies our constraints, whatever those constraints are. Like if it's supposedly sufficiently small, or we have tried enough values. So once we satisfy that, we give a solution. So now there are different methods, and here in the right, I show a little problem with some of the methods. They are local and global minima. So if you just follow the gradient, like for example, the steepest descent, and you are here and you follow down, you will find this minima. And so we see that gradient-based methods will tend to move to the closest minima, or to the minima in the direction of the slope. So if you are somewhere in the attractor of the first minima, you will never find the real minima, which is the global one, which is only in here. And this is a problem which most of gradient-based methods have, or actually all. For direct search messages, it's similar, but they sometimes are able, if you have initial values on both sides, to actually find the global minimum. Stochastic methods, stochastic methods are normally, they are sampling the whole space of parameters, and they tend to find the global minima, so they are far more computational intensive. And here are just a number of methods we provide in COPASI. All of these methods just basically give you the next best guess for the parameters. And then the evaluation is done by the model. So now coming to what we actually want to talk about in the rest of this hour, it's the parameter estimation. Note that in parameter estimation, the difference to optimization is that we do not have an objective function giving analytically or based on our model values. The objective function is actually the distance between observables and or observations, experimental, and values of the model we are looking at. So in general, it's a minimum. For each observable, we look at the distance to our simulated variable, and we sum up these distances, actually the square of these distances, and we try to minimize that. So parameter estimation is one special case of optimization where we just automatically generate this function, the objective function, as a sum of squares. Actually, it's more general, it's a weighted sum of squares, but in principle, that's what we are doing. And we can use all optimization methods, there is no restrictions. So with this, I'm gonna switch to actually do an example. I will start Copasi. My computer is a little slow. There it is. I adjusted already. Is the font good for you? Can you see it? I think everybody is muted.
Yeah. It's fine.
Okay, great. So I'm actually going to start with a model. If you have Copasi installed, you could do that later yourself, or you could follow if you like, because I have take one of the example in Copasi. So go examples, Copasi file, and I use a very simple one. It's called Brucillator, which has, we look at it, 6 species, of which actually only 2 are variables. The other ones are parameters or boundary conditions or clamped in the speak of V-cell. And so we have only 2 variables, X and Y. We have 4 reactions. We just use mass action. And so we have X, sorry, the order is not, so we have an external variable A, our parameter A, which leads to generate an X, then multiple X, 2X plus Y, actually generate 3X, X plus B goes to Y plus Z, and then X leaves the system. So if we look at the dynamics of the system, let's just to see that there's actually something interesting happen. We want to see it. I create a plot and I run it. Oops, actually I had already plots. And we see that the system oscillates. Here I actually created also a specific plot where I plot Y over X, and I see that I get oscillation, or a phase, a circle. Not a circle, a repeating curve in the phase space. So additionally, let me see, I can show you, I have experimental data, which is actually in the folder if you like to follow. I've opened it this is the data. I have time course data, which is actually some noisy data of input data for this system. It's a time course, and it's a time course which goes over from 0 to 100, and I recorded the concentrations of the variables X and Y, or species X and Y. So I like to do now, I like to fit my model to this data. So I go to the task, it's parameter estimation. And the first thing we really need to do is to define our objective functions. As I said, this is based on the experimental data. So we need to tell Copasi what is actually the experimental data for our, in this case. So I open experimental data. I'm presented with this dialog. And the data is in the file I just talked about. I can hit the plus button here. I add a data file. I'm going to be presented with a dialog. Actually, this is not the location. That's the location where the model was. But this is in documents. Where is it? It's workshop, parameter estimation, and it's called it Bruce noisy data. So I open that file. I see Copasi immediately determined, oh, there is one parameter experiment in it, and goes from row 1 to row 201. Actually, I found a header, non-numeric information in the first row, and the separator seems to be a tab. If you do have comma separated data, you can, or other separators, you can specify it here. And Copasi doesn't know, figured out the column names, provides me with them. It doesn't know what to do with them, or whether they are actually connected with the model value. So I have time. Obviously, time is time, so I should map it. I want to select, oh, I can't select time. Oh, what we see is this experiment type is steady state, but we provide a time course. So Copasi can map to two kind, fitting for two kind of simulations, which are steady state and time course. In this case, we provide Copasi with a time course, and we need to tell it. So it's a time course. Ah, now it figured out that time is actually mapped to time, but it doesn't know what X is. So X is a variable which is dependent. It's dependent on the model. It's a model calculation. It's one of the variables we actually want to fit. So I'll select dependent. I later going to explain for what I use the other type. And it's a species. It's a transient concentration. And in this case, actually the names match. It's X, but it doesn't have to. And you see Copasi determined automatically a weight for this curve. Now I do the same with Y. It's again dependent. Passing up. If it's dependent, I need to know what it matches to, and this is Y. Okay, and the weight of this curve is different. Why is the weight of this curve different? We want to fit both. Let me see if I have the plot still open. No. If we remember the oscillation, that one of the parameters is all the time very small, and only at certain values So in average, one of the parameters is a lot smaller, variables is a lot smaller than the other. Therefore, we try to keep them both on the same scale. And this way is automatically calculated based on the mean square of the curve. So now that we have the experimental data, I press OK. And the first thing is it's done. Now I want to estimate the parameter of this system. What are the parameters which I vary? And these are the parameter constraints I mentioned in one of the slides. So we need to specify the parameter or object which we want to vary or determine. So right now there's nothing. I use the Copasi button. This is, whenever you see that, this is a selection tool. And in this case, we are actually interested in the reaction parameters. If we look at them, let me put them all here. Each reaction has only one parameter, it's K1. So I could now add them individually. Okay, I can just say, I want all reaction parameters. I highlight reaction parameters and I hit OK. Okay. Copasi actually did it for each of the reaction parameters, K1 of reaction 1 to 4. And you see, we are very conservative. We have an extremely large bound here from 10 to the minus 6 to the 10 to the plus 6. In other words, it's spanning a scale of magnitude 12. Let's reduce that a little bit. So I could now go and say, oh, this is only -3. And you see, I changed it for the parameter, only for the first parameter. But for convenience, you can select them all, or you can select some. It's like what you normally do, control minus, control click, or shift to get all of them. So now I say the lower bound is 1 to the -3, and the upper bound is 1000. Okay, now the start value per default, that's one value Copasi uses in when starting the parameter estimation. Since these are the model values, it would be unfair to start with those. So I can now select a start value. Here we go to the start value. Note we still have all 4 selected. I click this the button with the 3 dots. It's a little small. I hope you can see it. But whenever you have this kind of button, you're going to be presented with a choice of what you want to do. So now Copasi asked me, oh, this start value, do you want to use the model value, the current solution? I'm going to explain that, or some random value. So I say it's supposed to pick a random value. So now we have a random value, and we are basically ready to see what's going on. But before we do that and do actually run the parameter estimation, I like to show, we also want to have an output, not just the data at the end. Let's see, one of the things you always want is a progress of fit that tells you how well, whether the parameter estimation proceeds. It gives you the function, the best function, the current best function value over the number of function evaluations. So if we create that one, and then actually we also want to compare our experimental data with our simulation data, and for that we pick the parameter estimation result. Now we have 2 plots to give us feedback of the result and of the progress. So let me explain what current solution is. So right now, the current solution is always the start value you see here. So if I run the current solution, that is, in this case, it's not meaningful, but if somebody sends you a COPASI file, you could look at their statistics which run without running their parameter estimation again. So let's just see that that actually works. And here let me disable this one. We don't need this one anymore. We deactivate and close it. And we deactivate because I don't want to see it again. And I also want to close it. So the progress of fit, of course, did not do much right now because we actually did not calculate anything. We just took the values. And here we see, let me hide all. So this is the experimental value of X, and this is the fitted value of, for the current value, X just basically doesn't change, at least not in the time well, in this interval. And if we look at the error, we basically see something is not right because errors should be randomly distributed if everything is fine. The same for Y. We have basically Y being 0. Okay. Now let's run any of the methods. So let's start with gradient-based method. So we have, where is it? Steepest descent we could use, which is very simple, and run that. We must be in a very stiff region of the parameter space because it takes very long to calculate for just 100. And that is done. So we see we actually got an improvement, but let's look at the result. To get that window back, I can select in COPASI, and there is the result. That is interesting. We basically, instead, we got a double period, but the values lying somewhere in between. So that seems to be a local minima. And if we look at the other value, of course, it oscillates too, but a far lower value. We could run that again. And what you normally like to do if you run it several times, you would randomize the start value. While we are at this, there's also create parameters. If you look at the model, there are parameter sets. And if you run multiple parameter estimation or with different data and run it over and over again, you sometimes want to, or often want to, remember your values from the last run. So it's good if you have at least confidence that your parameter estimation works, that you select that button. Or COPASI would then automatically create for each of the runs a parameter set with time step when it was created. And calculate statistics. I can show you what that means. It is per default on, but if you have function evaluations which are extremely costly, which means calculating one function or fitting it just to one parameter that takes minutes, calculating statistics can then take hours because we need to calculate derivatives for each variable or parameter. So let's look at the statistics. We have the objective value in our case was 271, which is obviously is not very good. And we had actually 400 data points, which are, remember we had the time course, which has 100, we went from 0 to 100, and X therefore we have 100x and 100y values. Actually, and probably, I think it was in a half step. So it's 200x and 200y values. And we did 1,300 function evaluation and how much it took. We can look at the individual parameters. We have a remainder of the lower and upper bound. Actually, if our parameter would hit one of the bounds, these values would turn red, so that you see that your constraints actually, that your choice of boundaries actually constrains the solution. Then we have the coefficient of variations for this parameter, the gradient, and the standard deviation with this action. We can also get the information about the experiment. In this case, we have only one experiment. And we see the contributions to the error from each of the variables. So the largest contribution is from X. We can look at the same way. This is per fitted. This is now split up per. If we have multiple experiments, this would tell you how X fares overall per experiments. We have only one, so it's exactly the same as the other. Furthermore, there is the Fisher information matrix, which gives you some statistics on how well how much information is in your data, and how well that data allows you to determine the parameters as, and the correlation, which is just based off the Fisher information matrix. But before let's go on and do a real, maybe we could continue that, or we try another. Let's do Levenberg-Marquardt, which is also a commonly used local minima finder. It's gradient based. We run it. It seems to be stuck somewhere. Oh, actually, sorry, it finished. My fault.
You can show how to find the window using the window menu.
Yeah, thanks. So parameter estimation, here's the result. This one came up with a damped oscillation as a result, but still period about twice as big as the other. And the same for the other variable. So let's try another algorithm. Let's try one of those algorithms which are not using derivative, but do not sample, but still based on knowledge about the values. So let's try Hook and Jeeve. And that was also very quick. And this increases quick, finds an increasing value, doesn't look very promising either. Let's pick a global optimizer, which we will see will take a lot longer. So therefore, I pull that one already. It takes a particle swarm and see what's happening. So we see it quite quickly also get to the range of what the others found. It's 275, which was the minimum closely to what we had before. It's still improving. Based on my experience, it will not find it either, but we could run it again.
Maybe if somebody has questions, this would be a good time to ask.
Okay. Yeah, there was a question about K1. Yes, each parameter, it's K1 of reaction 1. If we look at the reactions, there was a question in the chat whether these are different parameters. Yes, they are. If we look at the reaction, the K1 is specified local to the reaction as 1. And each reaction has a local parameter K1, reaction local. Thus, they are all different. By coincidence, they were all 1 when we started. So this didn't work well, so let's try it again.
Hey, Stefan.
Yes.
Do you always recommend running different methods and then taking the average?
I do not say running, taking the average. You run different methods until you find one which actually gives you a result.
Okay.
So in this case, we haven't found one yet. Which could be due to my initial value. That is pulling it close to a very steep local minima. But if you look, we're gonna find it. Or most likely.
What would we need to do to run this on the cluster?
Pedro mentions that earlier we have a server version, it's Cloud Copasi, which we are right now in the process of updating. It had been dormant for a while. It needs to be updated to new Python and Django versions and adapted to current architectures, which will allow you to upload a model, select parameter estimation, optimization, or all these kind of various kind of tasks, and say how many of those parameter estimations you want to run, and then it runs them in parallel. So in this case, here I have to wait for each one. I could actually on my computer run several in parallel because I have enough CPU power, but in generally it's not, sometimes you have, especially if you want to do statistics or what Sarah is mentioning, if you want to do Latin hypercube sampling or parameter scan over large values or determine parameter confidence intervals, then you would have thousands of parameter estimations to run, which is not feasible on a single computer. Then you would use and run Copasi basically multiple times on a cluster in parallel. Let me stop that. So here, if you are dissatisfied with the progress, you can always pause it or stop it. In this case, I'm going to stop it, and it stopped. Let me just do one thing. I have the suspicion that this one and run this one again. I tried that, of course, this morning several times, and it always worked immediately. Another thing, which actually, since it doesn't seem to work, and let's look actually at the plot once we get it.
Try a genetic algorithm.
Yeah, not that one. It's already done. I need more iterations. Let's look actually if anybody has a guess why we have so much trouble with it. If we look at the experimental data, let's hide all. We look at this experimental data. Why do you think we have so much trouble with fitting that? Is it just a 4-parameter system? Any guess?
Not at all.
The system is oscillating, and a straight line is a good approximation. If you get the wrong frequency, you are worse. And that's basically true for each oscillating system. So can we help? Can we do something here to get to the right area of parameter values? Yes, we can. We go to the experiment, and I know we had 4 oscillations. So let me limit the data actually to just 51 rows. So I reduced actually my data, and I run now this algorithm. Oops, something is happening. And if I look at my data, and it found it. The algorithm just a second ago couldn't find it, and now it was easy. So let's see, refine this. So we take this, which is a pretty good guess, and we use, for the start values, we now select current solution, take that one off, randomize start values, and we extend the data range back to 201. And run. And this is a far better objective value than we have seen before. Actually, starting from that value, probably our local minimizers would work even better. So here we say, visually, those 2 curves are more or less identical. And here too. So in that case, if you look at the 2 curves and see that they look very similar, then you would look at the error actually. And we see there might be still some bias. So it's relatively small compared to the values itself. So if I look at the measured value, the error is very small, but there is some bias. We don't get it right at the oscillation, at the peaks. This one looks pretty good. It's not totally around 0, but it should be randomly distributed around 0. I mentioned since we are already close to the minima, or at least I think we are, we could check that by looking at the results and looking at our parameters. Well, actually, they are not 1. So there seem to be something, a solution even away from 1, which does the same kind of oscillatory behavior. let's see if we can use something else instead of the genetic algorithm, which might have been, let's now do Levenberg-Marquardt. And since we do not randomize, we start with this parameters, set of parameters and run this. That was very quick. That looks better, at least for this one. It's closer to 0. It's still some bias, but the magnitude changed. We could use other local solvers or other thing. So parameter estimation is not straightforward. And Pedro mentioned yesterday, there is a no, or actually, was it Monday? There is a no free lunch theorem, so you need to work for it. So I'm in the way of your lunch hour now. Let me go to another example, actually one which came up during this workshop and especially during in the project time. We were creating a model based on a paper. Let me show the paper. That was this paper. And we already heavily annotated it. Actually, Shwada did this. We went through it, implemented this model first in vCell, and then exported it to SPML and imported it into CoPaSI. And I can load that to show you. I did that before, therefore it's in my, remembered in my list of models. For you, I actually, I don't want to save this now, so I discard it. This model is available under my folder so that you can play with it too. Try to implement this diagram. We created the reactions. They have rate laws, which are basically all just mass action. And to just see that there's actually something happening, I can run it. So we have dynamics. We just picked the same K forward and K backwards for all, K reverse for all of the kinetics. And we also can see that we have a steady state for the system. So it's well behaved. And then we went and said, okay, but we want now this to behave exactly like what they described in the model. For this, we had to go, as quite often, to the supplementary material. And there were actually results provided. And here we see two things. We have the fluxes. These are steady state fluxes for 3 conditions. For the default conditions, they call it parental, and with RAS activated or ACT activated. And you see that the flux, the intake of glucose is about twice as high when RAS or ACT is activated. So we actually have 3 experimental conditions, and you also see we have 3, these are, actually, wait a second, let me scroll here. I have 2 open. We have also the initial conditions, or the steady state conditions for
Concentration.
Yeah, concentration for some of the species in our system. And Actually, we treated that as initial conditions. It might not be right. So our first problem was we need to convert this information into something which CoPASI can understand. And for that, we created a spreadsheet in which we added the concentrations of all the species and the fluxes of all the reactions. So that's basically just some creative cut and paste or manually entering it. But then we did something different. We have additionally, these are actually 3 different experimental conditions. One with RAS act, where RAS and ACT are both off, and one where RAS is on, and another one where RAS is off. We need to tell CoPASI that these are actually different conditions, and we can. So we added these columns A and B, where RAS is off or on, and ACT is off or on. Now we need to add that to the model. If we look at our global quantities, like all our reactions, this is the import reaction. And the import is basically KFR 0. And we have a global quantity for that. And this now depends on whether we have the system activated or not. We already added a RAS on and an ACT on global quantity, but we need now make the import or the forward kinetic constant depend on that. So to do that, we do not assign it 360. We create an initial expression. And it's straightforward. If, and now I select, I use always this CoPASI icon, if the global quantity, the initial value of ACT on is bigger 0, or the initial value of the global quantity RAS on is bigger 0. Actually, I said 0 and I typed 1, so my typing is not well coordinated with my speech. If that is the case, it's, let's say it's 360. Other case, it's 180. And I copied that. And now there is a nicer display. So if the values is bigger 0, we have twice as much influx. If either one of them is bigger 0 as in the other case. So now that makes the reaction, the import reaction, which is 0. We are right now in the case where we have both off. If you remember when I showed you those values. So the forward parameter is 180, and if I turn one of them on, and go back to the reaction, it's 360. So now we have our model modified so that the input actually, the influx of the system depends on those 2 new introduced parameters. Now we are ready to do our parameter estimation. and we already specified the experimental data. Oops, I get an error. And it tells me, and you want to be, if you see that, these kind of errors when you go to index, it tells you that you have an incomplete data mapping and column 17 must be mapped. Okay, let's take care of that. Let's look what column 17 actually is. So you see we did already all the mapping. This is a steady state experiment, so we don't have time. And there is column 17. Kopasi complained about that. Yes, it says this influx from external glucose to pyruvate is a dependent variable, but we didn't give it any object. So we need to select one. It's a reaction flux. And actually it's a flux of reaction of R0. And I hit OK. And I think I'm at the end of my time. This is how far we got in the last 3 days, thanks to Shraddha and all her work. And it showed us some of the features or some of the creativity you need to do to use all the data available in papers. So the next step is for us to use, select the parameters which we want to fit, and then try getting to some more meaningful values than the one we are using right now. So I thank you all for your attention, and if somebody has questions, please feel free to ask them.
Hey, Stefan?
Yeah?
When you did the parameter estimation, this has to be done only when the steady state is stable? This can be done only when the steady state is stable?
No, your model doesn't need to have a steady state, but it better has, it has some parameters for which it will find a steady state. So if a steady state calculation fails, the objective value in that case would be set to infinity, and that parameter set is discarded.
Mm.
So it will eventually find a parameter set where there is, or hopefully find a parameter set where there is a steady state, and then it will narrow down on those. So failures are expected actually in parameter estimation. Failures also in time course integration are expected, because large parameters, we still have a range of 10 to the power 6 in the first one. So it is often, it happens quite often that a certain number of your test sets will fail, but that is no problem.
But I would add, so the question I think was whether you can do this on unstable steady states. But
yeah,
I would,
That too.
if that's the case, then the answer is no, because you are not going to be able to get data from unstable steady states. So they are unstable, and therefore in an experiment you will never observe them, because the exact reason why they're unstable is that the system will always diverge away from them. So even though it would be theoretically possible to do parameter estimation if you had such data, you are never going to find such data. So in practice, unstable steady states are not going to be able to be fit.
No, they are not observed. That's basically the case, or very rarely observed.